So now I'm just going to quickly go over the formulas. Light's other formulas. Yeah. So the fraction, you should know that the wavelength over the distance is greater or equal to 1 means more diffraction will occur. So where's an example question? I'll just make up one right now. So if I told you we had an experiment where we shone light through a slit and we got this pattern. One slit, okay, and that's the fraction. This occurs because lambda on d is greater than 1. Now if we increase the wavelength, what would happen to the pattern? Well, first of all, our ratio, lambda on d, would get bigger. Therefore, we would have more diffraction. Well, not more diffraction, but it would diffract wider. And this shape would go from being, it would make it wider. It would go from here to maybe something like that. Okay? So that's how you use that formula. C equals F lambda. This is probably one of the most important formulas, I reckon. But it's a way, if you remember, C is fixed. They always tell you the speed of light. So it's a way of converting your frequency to your wavelength and your wavelength to your frequency. So if you quickly have a look at it, lambda equals C on F. So we find that the longest wavelength would correspond with the shortest frequency, like the opposites, which would correspond with the lowest energy. The shortest wavelength would correspond with the highest frequency, would correspond with the highest energy. So the way we use this in a question is, say in this question 6 over here. This is a photoelectric experiment. Let's say it looks something like this. If we look at the question across, it says here, from your graph, what is the longest wavelength which would cause a photoelectron to be emitted? So when they say longest wavelength, I can also think lowest frequency. So what's the lowest frequency which would cause a photoelectron to be emitted? That's the same thing as the threshold frequency. Yeah, easy. That's a threshold frequency for which an electron to be emitted. So all I need to go back, it looks hard, longest wavelength, you just go back and look here and like, hey, threshold frequency is like 3.5 or something. 3.5 times 10 to the 14. So my frequency, my threshold frequency is 3.5 times 10 to the 14. And thus, I need to find a wavelength though. So I just have to use my formula. I just rearrange this. So I make lambda the subject. I have to take f across, so it becomes a divide, c divided by f. And we get 3 times 10 to the 8 divided by 3.5 times 10 to the 14. And presto, we have a wavelength. So that's how you do those kind of questions. By the way, this is not right. I just sketched that graph just there. But that's okay. You guys can figure out the rest. The same principles apply. And finally, 2 last formulas in here. This is a way of getting energy from frequency or wavelength, E equals HF or HC on lambda. And this is a way of getting momentum from F on lambda. And remember, these are all momentum of light, and this is momentum of energy, because these are all light formulas, which are different for matter formulas. So, figuring out energy here, we can try these 2 questions. I'll find a way to show you this at the same time. How does that look? Okay. So we have an X-ray and we have a frequency. It's good to write that down as well. What is the energy in units of electron volts of 1 photon of these X-rays? Well, easy. Just let me figure out what H is. Planck's constant. I'll be back with you in 1 second. Okay, I'm back. Okay, so we want energy. So we want energy, and we have frequency. So we look for a formula that goes, hey, this is a way of getting energy from frequency. E equals HF. Of course, if it said wavelength, we could also use that. C equals HF. So now, they want this in electron volts, so we just have to use H in electron volts, which is 4.14 times 10 to the negative 15 times our frequency, 1.4 times 10 to the negative 10. And that'll give us our answer. So next one. What is the momentum of one of these X-ray photons? Well, we just have to use our momentum formula again. So this is a way of getting momentum from frequency and wavelength. So if they told us the wavelength, we could use this one, but they told us the frequency. So we have momentum, P equals HF on C, equals, and now we want it in kilograms meters per second. So we don't want it in electron volts anymore. So we have to use the proper H or the normal one, which is 6.63 times 10 to the negative 34, times our frequency, divided by the speed of light. I think it's 3 times 10 to the 8. And that will give us a momentum. So very easy, just 4 formulas for light. The fraction, the greater this ratio, the more diffracted it is. F and lambda is away from converting frequency to wavelength and back. And we have an energy formula, and we have a momentum formula. So whenever you see energy, think energy formula. Momentum, momentum formula. Okay, great. So that covers light's formulas.